Okay, hello everyone. Welcome to the last of the B sessions for our summer school this week. On that note, I wanted to take a second to just thank the organizing committee who helped put this meeting together, as well as other members of the Rubin Community Science team and especially Greg and Tina, who led some tutorial presentations. So thanks for everyone. I think things have gone really well this week. And thank all of you for attending, of course. Today, we will have one tutorial, which will be led by Ryan, showing you how to extract and work with variable star light curves from the catalogs that are available. So I think I will just, I don't think I have any other announcements, so I'll just let Ryan take it away.
All right, thanks, Jeff. And hi, everyone. So I'm Ryan Lau. I'm also a member of the Rubin Community Science team. I'm a staff astronomer at NORLab based here in Tucson. So yeah, I've been mainly attending the morning sessions here. So I think this is the first evening session that I've been to. But yeah, it's nice to get a chance to share this notebook with you all. Okay, so let me share my screen and then I can go ahead and get started. All right, so what we're going to do is we're going to go to data.lsst.cloud. That's our first step. And then we're going to open the notebook aspect of the Rubin Science platform. So you just go ahead and click on that. And then if you have if there's a prompt that comes up for a container size for your the notebook or this notebook aspect that you're running, make sure you check medium, because I think it might not work for a small container, or it might. I'm not sure. I haven't quite tested that out. But it for sure will work if you choose medium. So to navigate to the notebook that we're going to do, which is 07B, you're going to go to your home directory and then go to notebooks and then tutorial notebooks. And you're going to just double click 07B variable star light curves, and then that'll pop up. So I already have it loaded on another browser tab, so I'm going to just switch over to that. So it should look like this. You should have, see this window here. And if you don't, let me know. And if there's something looks weird, let me know. We can try to troubleshoot that. Okay, so I'm going to full screen this, and I'm going to get rid of this sidebar here so we can maximize the screen size. And also, if the text here is too small, let me know also, and I can zoom in, make it a little bit bigger if people would prefer that. Yeah, if not, let's go ahead and get started. So this notebook was made by Jeff. And then I've also added some edits to this myself to do add some of the different catalogs to study variable stars. So the purpose of this notebook is to see what a variable star looks like in these different catalogs. So you're going to hear me talk about like an object catalog, force source catalog, CCD visit, DIA object, DIA source, and force source and DIA object. The main ones that I'll be talking about are DIA object, DIA source, and force source on DIA object. So these are all different catalogs that produce the properties of difference imaging analysis, which is what the DIA stands for. A helpful link to have if you're curious about the products of these catalogs is this page here. So this is just a schema page to all of these different catalogs that I just mentioned. And if you're wondering like what any of the values or the properties that are associated with each of these tables, you can search through here, and it's a super valuable resource when you're trying to write your own code to find things or to understand what things mean. So let me go ahead and put that link in the chat. Okay, so yeah, the purpose of this notebook is pretty much to demonstrate the like the table access protocol service to query time domain products and to study variables. So there's another notebook, 07A, that's more focused on transients in the DP0.2 data set, specifically type 1A supernovae. But this one focuses on variable sources. So what we're going to do is we're going to look at a known, I guess, our library variable. We know what it is because we've identified it from a sort of a truth table. And we're going to look at that source, and we're going to study its light curve and demonstrate how we can use these different tables to produce light curves of these variable sources and to run some kind of period fitting or period finding Lumskargel analysis on it. And then we're going to see in section 3, we'll demonstrate how we can use the tap searches and these difference image analysis catalogs to find these variables. So something to keep in mind as you're going through this is how you might adapt these searches to identify other types of transient or variable sources that you're interested in identifying, if it's based on their amplitudes or their variability periods or things like that. So that's this section 3. We'll go through how we actually find those. And then towards the end, we'll get into some subtle differences between using the different catalogs to analyze these variable candidates when we identify them, and some differences in kind of things to be aware of when you're doing analysis and how different tables can affect your results. So it really is kind of you'll get kind of an in-depth understanding of the differences between these different catalogs. And pretty much the main ones that will be brought up in this notebook are the DIA object catalog, the DIA source catalog, and the for source on DIA object catalog, or tables. I guess, yeah, I'll use tables and catalog kind of interchangeably. So instead of kind of explaining exactly how these connect to each other, let's just run through this. And then I think it'll become more apparent as we go through this, how these catalogs kind of, how they relate to each other. Okay, so let's start off with importing our packages. So we'll just start off here, just some basic package imports, a lot of AstroPy stuff. So for example, the Lumskargel is what we're going to be using to do the period finding. And we're going to be using the TAP service to do the searches through the Rubin Science platform for our candidate variable stars. Here is just some plots parameters to make our plots look nice. And also setting up the different filter bands in our plots so we can have each UGR IZY band to correspond to a certain symbol and color that's kind of defined here. All right, and then this cell, we're going to start up the tap service. And okay, so section 2, we're going to start off with creating a light curve of a known R library variable. And as I mentioned earlier, we know this is an R library variable based on the truth table from the simulated data set. So it's basically, we already know what this is, but we're trying to kind of demonstrate the capabilities of these different tables and how we can use this to study a known variable source, as we would for like a real variable that we identify with Rubin data. Okay, so first we're actually going to do extract force photometry measurements of this variable. And so we're going to give it certain coordinates here. These are the known coordinates of this R library variable. So we'll just define that here. And then in this query, what we're going to do is we're going to run this tap search through the object table catalog. So that catalog is essentially, you have some astrophysical source that's associated, that gets identified as an object. And then in every visit or every time, like Rubin takes an image of a particular point in the sky, there will be a source that gets identified, and whatever object that source happens to be closest with, it will get associated with that. So we're going to look through the object table for the this particular variable. Since we know its coordinates, we're just doing a search through this object table with a very small area. And we're going to get some of these properties querying from that table. So we're going to get the PSF flux at the G band, the R bands, and the I band. And we're also going to look at these other parameters here, the extendedness parameter, which will be helpful for us to know if it's a variable source or not. That's one of the things that you can use to see if it's like, maybe it's a galaxy that's got some AGN activity, if it's extended or not. So we're going to execute this here. And before I go on, I'll mention that this is at the point where it's really helpful to have this schema available. So what we're doing is we're querying the object catalog. So what we can do is go here and then look at object, and we can search through any of these column properties here and use this in our tab search to constrain our search or to look for anything that might fit the parameters of any of these particular columns here. So there's a lot of flexibility to kind of tailor your tab search to whatever you're trying to find. So it's definitely worth taking a look at this and seeing what parameters you can use to narrow down your search. All right, so we executed this, and here's this particular line here. That's where we're constraining the this kind of cone search to this with the circle of this particular radius, so 0.001 degrees. All right, so let's look at the output from this tab search. Here's the table, and here's all the stuff that we requested from it. So all this kind of stuff here. And we also convert from PSF flux, which is given in nanojanskis. Like if you look at the schema, GPSF flux is given in units of nanojanskis. So I sometimes prefer Janskis, but I know lots of supernova and variable star people prefer AB magnitudes. So we'll be converting to those. And that's, these are the values that we have here from this table. So you can kind of see all of that here. And also you can see the extendedness is 0, which is good. So we know it's like an unresolved source there. Okay. So yeah, I'll stop here for a little bit, and I'll see if anyone has any questions or anything that's any issues with getting this started or running any of these cells. All right, so let's continue. So we'll go to section 2.1.3. And then we'll extract the measurements from this forced source, or from the forced source table. So what we're going to do is first we look through the object table, and we use this to get these properties, and then also to get the object ID. So our object ID is here. It's this long string of numbers. So we're just defining this variable here, select object ID, as the object ID here. Okay, and now what we're going to do is we're going to do another search through the forced source table. So this forced source table is going to give us the forced source photometry at the location of this object that we give it. So forced source photometry, that all that is it's going to it runs, or the pipeline, LSST pipeline runs this forced source photometry where it's given the location or an RA index coordinate, and it forces a PSF fit to that particular location at every single visit that includes that particular coordinate. So it's useful for looking at something that's like a variable star that you might want to have the entire time coverage to look at. So that's what we're doing here. We're going to get these values from the, let's see, from these tables here. So let's do this first. And let's see, I guess this one, we're looking at the object ID from the force source table. So this is what we're calling as SRC. So these values are what we're getting from the force source table. And then we're also getting the CCD visit info from the CCD visit ID. And that's useful for grabbing the CCD visit ID. Let's see, from this table here. Or actually, you can get the CCD visit ID from the source table. So now I'm wondering why we're also getting it from the CCD visit table. Okay, yeah, I'm not quite sure, but I guess it's good to have to double check that you have both of those things there.
It's actually so that you can get the time of the observation, because that's in the CCD visit table and not in the force source.
Oh, okay. Okay, that makes sense. And so that time, it comes from here. Oh, I see.
Yep.
Oh, okay, that makes sense. Sorry, we're doing a table join here to to extract the time information from the CCD visit table. Yep. So so we'll execute this here. And then we'll do the run the query in this tab here. Yeah, thanks for the clarification on that, Jeff. Yeah, I got kind of confused on that cell there. All right, and then we have 432 measurements corresponding to that particular object that we searched. So this RLRA variable has 432 force source photometry measurements. And we can actually see what this table looks like if we uncomment this line here. And you'll see that, we didn't restrict it to any particular band. So I believe, or maybe we did. Oh yeah, I think we're just looking at, I don't think we restricted it to any particular band. We're just looking at the PSF flux from all of these. So this is all provided here. And then I guess for things with duplicate values, you see a little 2 there. So like how we requested CCD visit ID from both catalogs, the duplicate has a 2 by the side, but they should be the exact same. All right, so essentially this is our light curve table here. We ran a search for the object ID initially, and then we used the object ID to identify the force source photometry associated with that particular object at that location. So all the light curve information would be from this table here. Okay, and then now we're gonna create a phased light curve, or first we're gonna select the photometry from each band. Since it's all in this table, we need some way to kind of parse that out. There's different ways to do it depending on how you like to use Python. So in this cell, we're just going to do this kind of define this function here to sort through the different bands and identify which filter is being used for each thing. So we can plot this for the R band. So for instance here, we're picking the R band filter, and then on the x-axis we're plotting the x midpoint MJD. So essentially the time that MJD date that the observation is taken. And then on the y-axis is the AB magnitude here. And I guess, right now it's plotted with in the other opposite direction. So we can also try to invert that if we wanted to. And so, clearly looks like a variable star. So that's good to know that we've double checked and we've found, or that we've identified, or that the source that we're grabbing was indeed a variable. And then, okay, so this next section here, we're going to take this and then we're going to create a phase light curve based on that force source table that we've created. And then I guess, it's important. There's a caveat here. This is just kind of to demonstrate one way, a somewhat simplistic way to do this kind of variable star analysis on this kind of light curve. So it's just demonstrating how we can use these time series data to how we might, one way to do this kind of time series analysis, which is to create a phase light curve and run the Lumsgargle package from AstroPy to identify a period. But there may be more sophisticated ways to try to do this. So that's a thing too. If you're interested in variable stars or RLI arrays, you can probably have your own input your own code here to try to do a more rigorous study of the period and variability. All right, so here we're just going to read in some of these values here. So we'll have MJD days as the time or the time sort of table, and then mags as the brightness. And we're going to use this to run the Lumsgargle algorithm to find a period. We'll define a minimum and maximum period because we know we have an idea of how long we expect our RLI variables periods to be. So they can range from kind of 0.2 to 0.9 days. So this will help run the period search. Okay, and then we'll just run that here. All right, and this next cell will output essentially what is the peak frequency, or what frequency has the strongest power in the spectrum. So you can see here, these are the results from each of the bands, the UGRZY. So they're all super consistent, which is good for the peak frequency. And then the period here is about 0.5 days, which comes from the mean of the frequencies that we identified from each of the bands. So that seems pretty consistent with the range that we would expect. I mean, we did also specify that it needs to be within 0.05 to 1 day. So we expect it to kind of be in there. All right, and then in the next cell, we can take this, take what we know, just I guess demonstrating that this is what the power versus frequency looks like in the periodograms here. So just to show where the peak frequency is and what period that corresponds to. So this is just the output from the Lumsgargle analysis here. All right, and then we can create a phase light curve. So we can do that by first defining what the best period is, and which is just 1 over the frequency. And we'll define that here. Essentially, that's just this value, this 0.5 days. And then the way we define the 0 phase is somewhat arbitrary. We'll just say it's the minimum value for the earliest measurement, I guess, of the G-band, a G-band flux that's measured in the force source table. So this can be definitely tweaked around, but kind of just arbitrary to establish a T naught for defining this phase light curve. So that's just what this cell is doing here. Right, and then we can plot them separately using this nice set of code here to kind of get a good spread of, let me zoom in a little bit too, or to show each of the phase light curves at the different filters kind of spaced out by one magnitude. And then these dash lines here, I believe, are showing the mean, the mean magnitude of these, where the mean magnitude is located for each of these filter bands. And also we can plot this all together. That's just what this cell is executing here. So here they all are. It's interesting. You can see different shapes depending on the type of filter that's being used. So you can imagine that you can also fold in color information. They could color plot based on the phase light curves. And I'm not an expert on RLI variables, but perhaps that can tell you something interesting about the source. Or for variables that you are interested in, you can do that kind of analysis with all these different, all the different color information that you have here from the 6 filters. Cool. Okay, so I'll pause here for a little bit. The next part is we're going to go searching for RLI variables, so how we can find certain things from these different catalogs. But I'll pause here to see if there's any questions or any issues with anything that I just went over. Okay, let's see. Cool. All right, let's move on then. Let's go on to section 3, which is how we identify candidate RLI array variables from these different catalogs here. So instead of using the object table, which is what we did in the beginning, or the source table, you're going to need a table or a catalog that tells you what's time varying. And so now we're using the data products from the difference imaging analysis, so DIA. So we're using these particular catalogs here, the DIA object table, DIA source table, and the force source on DIA object table. And so here's just a quick definition of these things here. The DIA object table, the way that I like to think of it is like the DIA object table is like that's a particular like astrophysical source. Like you have one object, DIA object that's equivalent to like this like a single variable star or transient. And then DIA source, this is the table of single detections of a DIA object in a difference image. So for example, a DIA object will have multiple, like could be hundreds of DIA source measurements on them, depending on how bright it is, depending on like what filters are used and the coverage and things like that. And then the force source on DIA object table is it's the force photometry in every single visit image of that DIA object. And the difference between the DIA source table and the force source on DIA object table is that the DIA source table only produces a quantity if that source is greater than 5 in signal to noise ratio. Whereas the force source in the object, you're going to get photometry from it, force photometry from it, no matter what's there. So even if it's less than 5 sigma, even if it's not there, the pipeline is going to try to force a PSF fit to that source. So this is really, you get everything. It tries to fit everything that's there in all the difference image data at the location of a DIA object. Okay, so now what we're going to do is we're going to use the DIA object table and the force source on DIA object table to retrieve candidates and also photometry. And we're going to do this based on some criteria that we apply to a search. So to find things that seem like RLI array variables, we're using these parameters here to constrain our search to try to identify these. So we're just looking at G-band just to make things a little easier. We're going to do a coordinate search. So we don't have a particular, we're not going to search through the entire sky, but just sort of 5 degrees within a chosen RA index position. We're going to look at the scatter here of the sigma to the mean flux of the total flux. So we're trying to look that the scatter measured flux is larger than 25% relative to the mean, but no larger than 125%. So this is kind of just constraining the amplitude of the variability here. Here, and then it's just the mean magnitude is between 18 to 23 to kind of restrict the ranges of the magnitude of the sources that are the candidates that we're going to get from here. 6 is the number of G-band detections we're requiring for us to see for this target. So we want it to be fairly well sampled, which is why we're setting this requirement. And this Stetson J index greater than 20 here. Yeah, I don't quite remember what the statistic is here. Very explosive. Okay, so it's just high values of this index should identify objects whose fluxes vary more than expected. So another indicator of variable stars. All right, so I won't go through too much. I won't walk through this particular search here, but essentially we're doing exactly what we're trying to do with applying these criteria to find these objects in the force source on DA object catalog and also the DA object catalog. So this is like a kind of a multiple table join function that we're doing to get the properties that we want out of each of these tables. So if there were these quantities or these values that we're looking for in a single table, we wouldn't need to do this table join. But since we're grabbing parameters from different tables, that's why this search here is a little more intense. So we can just run this search there, and then it should be done pretty quick, like less than a second. And then we saved it here in this for source on DA objects, or FSODO, which is short for for source on DA objects, source results kind of table here. So what this is going to provide is all the DA object IDs here, and also the different parameters that we have for that we specified here in this search. And then each of these things here is going to tell us like the number of DIA sources associated with a particular DA object. So has all those values there. What might be nice is since you can see there's duplicates, we can just look at the unique number of DA objects. So it looks like it's about 14, where this is the total number is 702 in this table, but the total number of unique sources is 14 here. And then we can plot that here. And these are our library variable candidates, the different DA object IDs and their coordinates here. So just as a refresher of what we just did, we did a search, like a 5-degree search. Let's see, do I remember that correctly? Yes, so we searched 5 degrees around a given coordinate position. We specified these criteria, and then this is the output, ultimate output from that search. These are our candidates that came up from that search that we did. There is kind of an interesting caveat here about doing this. There's an issue that we've kind of identified, that's, if you remember, I mentioned earlier that I like to think of DA objects as that they are equivalent to like a variable star, like that RL array, that's DA object, The problem is that through some issue with the source association algorithm, you can have multiple DI objects associated with one like astrophysical source. And that issue is actually quite prevalent here in our data set. So some of these sources might actually be, I think, the same actual variable. So it's just something to keep in mind. And we're working on ways to kind of investigate this and see if there's obvious ways to distinguish if you have two different DA objects that are actually associated with the same source. But just something that's like, keep that in mind as you kind of go through this and as you go through the DP0 data set. But it's something that, it's something that we're working on to see if there's a better way to, or a good way to know when that is going to be affecting your statistics. So, okay, I guess a good example of that is this. You'll see here, these are have two different DA object IDs, but if you look at the RA and DEC, they're like the exact same. So something weird is kind of happening here. We're taking a closer look at this to see like how and why it happens. Okay, I went through this, or went through kind of a lot of this here. So I'll take another short pause to see if there's any questions. Okay, question from Tanaza. Shouldn't RA and DEC be the same in that case? So if multiple D objects are from the same source? Yes. So that is one way to really look at this, is to see if their RA and DEC is like super close together. And it's like, oh, you're probably dealing with the same actual astrophysical source, but have multiple DA objects. But sometimes if you're dealing with a really crowded field with like maybe lots of variable stars, you might need to have like a better way to refine that criteria than just looking at purely coordinates. And if you're doing that for like thousands of objects, we're trying to think if there's like a better way, if there's like a flag that we can have to indicate that maybe this object is not associated with that, or that it's associated with this other one here. So just something that we can identify if there's two DA objects that might actually be the same object. But yeah, you're right that the coordinates should be very similar, and that's definitely one way to diagnose it. But then if you have something that's maybe a chance alignment between two things, like a background galaxy and then a foreground star, you can imagine how that could also cause some potential issues with that here. Okay, so question from Ilya: why does the initial table return 50 plus versions of the same DI object? Yeah, that's a good question. So let's see. I think what we're doing here in this table is it's outputting, it's just searching for a DA object, and then also I think what we want is, yeah, is also the time of this observation here. So since we did a kind of a complicated like table join in our search, what we really wanted is also the temporal information too. So this also contains the different flux measurements at each visit of this source. So we're doing kind of a lot here in this search, and that's why there's multiple DA object IDs that are popping up in here. So not each of these correspond, or that's why there appear to be duplicate DA object entries here, but they all correspond to different measurements from the force source on DA object table. So this is all force source photometry on the difference images in each of these. Each of these 30. There's 37 of these associated with this. So yeah, sorry, I didn't quite wasn't super clear on that, but yeah, it looks a little confusing here. Perhaps there's a better way to demonstrate this, or maybe to break it down into smaller tables where it's more clear what we're trying to do, because this is, it's a pretty big table that we just made. Okay, good question, Tanasa. So they're asking what's the benefit of force source on DA object over DA object. We'll get to that here, and that's one of the points here in this notebook, why you would do force source on DA object over a DA object. But what it comes down to is that you'll have more, I guess, photometry in the force source on DA object table, because the DA object table, those are only detections that exceed a threshold of signal to noise ratio of 5. So if you're looking for lower level variability, like, I don't know, signal to noise of 3, or you want to have like good maybe limits on what your source is, and at previous times if it's a transient, then you would use the force source on DA object table. It just gives you more information than the DA object table. But if you're trying to find something interesting, like a variable that has a significant or high signal to noise, you're going to use the DA object table, because force source on DA object is it's kind of overkill for those purposes. Yeah. Okay. Yeah. So transient. That's the key thing here too. So like if you're looking at a supernova and you identify it from the DIA object table, but you're like, oh, this is interesting, maybe it exhibited some kind of past variability, then you would search through it on the force source on DA object table, and then you can see if it did anything interesting, like any past variability, like if it had some like a red supergiant that was doing something cool before it exploded. You could use the force source on DA object table to look for lower level variability, to see if it did anything interesting there. And then in this notebook, I'll also show why, or the differences that you get in doing, in getting photometry from the DA object table when you're looking at a variable star compared to the force source on DA object table. So there'll be some subtle differences and some not so subtle differences in the light curve analysis here, even for variables. Yes, and then if you are interested in the force source on DA object table, So this is a point that Greg just made in the chat, that you can look at notebook 07A. And that one goes through essentially what I described. If you identify like a supernova and you're trying to look for any kind of variability, beforehand, you can do the force source and DA object analysis. That's in 07A. Cool. All right. So now what we're going to do is we're going to stepping back here to where we were. So we have our 14 candidate variables here, and then we'll run the Lumsgargle frequency algorithm on all of these candidates. So that's just what this cell is doing. Let's see, I'm not sure how long this, oh yeah, that's pretty quick, like 4 seconds. And then we can plot the light curves of just a couple of these candidates here. So just to see like maybe 3 of these, we can plot the phased light curves using the same kind of code that we used in the section 2 to study that single R Lyrae star. And we can take a look here. So this is the mean flux here. This looks pretty R Lyrae like. It's got a period of about 1 day. Here's another one here that looks a little weirder. Maybe a little more sinusoidal variability, has a period of about 0.27 days. And then here's another one here. I think this might even be the source that we were looking at in the beginning. It's got a period of about 0.5 days. So it's a nice phased light curve here. Yeah, oh yeah, so this one here is indeed the same one that we did in section 2. So that's a little bit cheating, but that's definitely an R Lyrae variable. Okay, so now, we're getting to the point of what's this kind of, I guess, cautionary tale-ish kind of thing when we're comparing the light curves of the force source on DA object versus DIA source or the DA object table. So what if we just used the DIA source table instead of the force source on DA object for looking at these variable star light curves? So you can kind of go through that thought exercise in your head, like, what if we just use the DIA source table or the DIA object table to get the DIA source measurements of these variables? Well, there has to be some reference template that's being subtracted to identify these variable stars. So you can imagine that if the particular phase in variability that star was in, if it's close to that reference level in that reference template, you're not going to get a very high signal to noise detection. So you're going to miss that source in your DIA source table because it doesn't exceed that 5 signal to noise ratio threshold. So that's essentially kind of giving away here what's the key difference in using force source on DIA object versus DIA object or DIA source. But let's go through that exercise here to look at this more closely. So here we're just using the DIA source instead of force source on DIA object, but doing the exact same thing that we did in the previous subsection. Okay, so the first thing to notice is that the length of this table is shorter. There's 549 measurements, whereas our force source on DA object table had 702 measurements. Although we have the same number of unique object IDs, which is good to know. We're not missing any candidate from doing this search. So now let's repeat the same Lumsgargle analysis here in this cell using the DIA object table instead of the force source on DIA object table. And yep, just took like less than 4 seconds. It's pretty nice. And then let's plot these things here. Okay, so this will kind of demonstrate the differences if you're running this analysis on photometry from the DIA source table versus photometry from the force source on DIA object table here. So this particular one, there doesn't appear to be too many differences between the period that's found using the different tables, because you can see here the number of sources from the DIA object search versus the force source on DIA object search is the exact same. So you kind of just got lucky where all of the visits had a DIA source flux that was greater than 5 sigma. So this looks almost exactly the same here. I guess it's interesting to know too that there's some differences in this in the photometry here. Like it's not exactly the same, and I think that's because the the way that the four source photometry is done is fit in like a slightly different way. So four source PSF photometry versus some other type of photometry that's or slightly different photometry that's performed on the DA object, which I'm not quite sure of what exactly is causing that distinction, but it's kind of interesting to note. Right, and then this one here is you can really start seeing the difference. So here in the four source on DA object table, this thing had 50 measurements, but in the DA object table, there's only 36 measurements. And this has caused kind of a drastic difference in the period that's found by just using the measurements in the DIA source or DIA object table and the period that's found from the four source on DIA object table. So this is kind of like kind of a warning here that this there's something that there is this discrepancy depending on which table you're using. This one here, the phase is just different, likely because of the different number of detections and likely because of the way that the T naught is defined. So the period is almost exactly the same, but it's just I think it's just at a complete flipped phase. So not significantly different in terms of just overall analysis, but just some slight subtle differences that you can get using one table over the other. And you can see that the number of sources detected in each thing is pretty similar here. I guess, yeah, to look at this a little more, you might wonder like what table do you use if you want to do this kind of analysis? So I would think that the four source NDA object one is the thing to use for variable stars if you're doing some kind of period analysis. But it's also important too to, I think, inspect a little more closely what sources or what detections didn't make it through the DA object table, because they are intrinsically kind of lower signal to noise if they're not appearing in the DA object table. But it's just interesting to look for kind of I think the most robust thing that you can have is if the DA object table and the four source and DA object table are telling you the same thing. And that if there's something weird going on between the DIA source and four source on DA object like curves, then that's something to take a closer look at. So, all right, you might be wondering like how significantly can this affect your sources, or how frequently do you expect something different, a different result to occur in an analysis of variables between the DA object and four source on DA object tables? And that's kind of what we're trying to do here. So estimate the fraction of candidates that have different periods. So it's like 70% of them look like they have different periods in both of these tables. So in a majority of sources, the four source on DA object tables and the DIA source tables will say something, give a different, provide like a different period or variable source analysis. So yeah, that's kind of an important thing to keep in mind. And then this is just kind of to demonstrate this and how much this can affect the periods. So you can get some pretty significantly different periods here. This is just 1 hour. So a lot of other things are kind of within like an hour-ish of difference using it between the different tables, but some of them are pretty substantially different. All right, so yeah, that's pretty much the end of this notebook here. That's I think the key takeaway from this is, well, I guess first of all, it's kind of a demonstration on what the Rubin science platform can do and what's available to currently do with the DP0.2 data set. The simulated data, there's like 4 different types of variables, I think, that are currently simulated. There's in terms of transients, there's type 1a supernovae. So you can kind of test out different code that you might have or analytical techniques that you might have on the existing data set, and then see how it runs with that, and then kind apply that to when real Rubin data come out. But yeah, it's just a nice way to see the capabilities of the Rubin Science platform, particularly the notebook aspect and the kind of the level of analysis that you can do with the data products that are going to be available. Yeah, and then just again, like thinking of ways that you might apply these techniques to your own scientific interests to study variables or transients. And I guess another takeaway from how to do this, or what I would take away from this notebook, is that if you want to find variables, you would want to use the DIA object table to find them, and then to characterize them, I would use the force source on DIA object table. That's kind of the what I would say the messages from this, because you get more measurements with the force source on DIA object table. Cool. All right. So yeah, I want to thank you all for your attention and the great questions. I know you're happy to take more. Yeah, if not, you feel free, if there's something later that's on your mind about this, you can ask a question in either the chat or on the Slack workspace, or send me an email or something, and then I'd be happy to answer it then. If anything, if not, I'll just hand the floor back to Jeff.
Yeah, thanks, Ryan. Another thing I would add regarding this notebook is that I'm not an expert in variable stars. So I know that, some of the analysis that I did, like the Lomskargel stuff was just me testing to see whether I could figure that out. So if any of you are experts in variable star analysis, you can probably do a much better job than what the initial version of that notebook did. And welcome to do so and share it in the delegate contributions repository, for example, so that others can see a better way of doing things. But it does at least gives you an idea of the types of data products that are there and how you might get started doing some analyses. So now we are scheduled for a break. So we will take a 10-minute break, and then, as we have been doing, return and move into breakouts to work on projects or explorations together. So think of what you are interested in working on today, and we'll go take a 10-minute break and come back at 5 past the hour.